Testing. 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 Alright, we got it. We're going good. Welcome to another stream. Good morning and happy Thursday, I guess. That's what it is over here in Texas. So we're going to be doing a paper reading today. Thanks for the Discord community for choosing this paper. If you have other papers you want, you should go onto the Discord community and post them, and maybe we will end up reading them. So this is a paper called MegaByte. It's coming out of Facebook AI research, or I guess Meta AI. I don't really know what the different groups within Facebook are at this point. I don't know if Meta AI is the same thing as Facebook AI research and they rebranded, or whether they're kind of two different things, or I don't exactly know. But 12th of May 2023, so really recent paper. And this paper I think became popular after Andre Karpathy, Twitter, posted about it. So yeah, I forget exactly, but right here, yeah, he's called it promising. So everybody's kind of looking at it. And one thing I noticed, I was looking at these authors on LinkedIn, and some of them are already left. Yeah, look at this. So this guy here, he used to work at Facebook, but now he's gone. Now he's at a stealth startup. So we'll see. I suspect that there might be a startup that basically tries to use this strategy, but I think they're going to run into the issue where they're not going to have enough money to train anything big enough. But okay. So we have a paper with some interesting authors, with some interesting attention, and coming from one of the big companies. So let's see. Let's see what it's all about. Autoregressive transformers are spectacular models for short sequences, but scale poorly on long sequences, such as high-resolution images, podcasts, code, or books. Okay, so high-resolution images, podcasts, code, or books. I guess what they're really talking about there is that the sequence that you can put into a transformer is fundamentally limited by the amount of memory that you can use. So let's do this. Transformer attention. Here we go. Transformer attention mechanism. Yeah, so whenever you're doing a transformer attention, that's not the picture I wanted. Let's go back. Let me find the right picture. You're multiplying the sequence kind of largely by itself, and you're finding which parts of the sequence attend to which other parts of the sequence. I feel like this image is probably the best right here. So, right, people call this quadratic because it's a square. So let's scroll back up. Where's that image? Here we go. So you see how this is the sequence, aka the sentence that's going into the actual transformer, and this sentence here says, it requires enormous amounts of resources to achieve high scores. And what the attention mechanism is doing is it's basically looking at what each word attends to. So every word has either a high value for similar words, so requires enormous, you see how requires and enormous have kind of a high attention to each other, but requires has a very low attention to the word high, right? And the word it has very low attention to pretty much anything else other than the word it and requires. So the length of the sequence defines one of the sides of the square, so as you increase the size of the sequence, you're increasing the size of the square, and the amount of memory is the area of the square. So that's the biggest problem with transformers. We propose MegaByte, a multi-scale decoder architecture. So multi-scale here refers to the fact that there's going to be potentially, actually, before I say anything, let's just keep reading because it might not be the type of multi-scale that I'm thinking of. Decoder architecture that enables end-to-end differentiable modeling of sequences of over 1 million bytes. So bytes is 8 bits, and it's a kind of a way to measure memory inside a computer. So if you know what a floating point 32 is, or like an int 8, right? An int 8 is 8 bits, floating point 32, 32 bits, and then bytes are each 8 bits. And generally, you can represent most characters as a specific byte. So you see here, I guess in this picture here, this first letter M would be 1 byte. MegaByte segments sequences into patches and uses local submodel within patches and a global model between patches. Okay, so we're starting to get an idea of what they mean by multi-scale here. You're going to have different size models here. You're going to have a model for the local, which means closer to the sequence, right? Closer to the input. So you see here, I guess they have the actual sentence MegaByte transformer, and then you see how there's like a little local model that's very close to the input. And then you have a global model that's much further away from the input at a higher level, right? So that's the multi-scale that they're referring to here, is the fact that you have some things that are close to the input, right, at the lower scale, and then some things that are further and further away from the input, right? There's more layers in between the global model here and the actual input. This enables subquadratic self-attention. Okay, so subquadratic, right? That's referring to the fact that normally attention mechanisms are quadratic. Quadratic is just, quad means 4, and it comes from the fact that it's a square, or a rectangle, I guess, no, definitely a square. So the total area of the square scales quadratically with the length of the side, right? Because basically the length of the side squared equals the area. But because they're going to be doing some fancy stuff here with the local and the global model, it's going to be subquadratic self-attention, which is important because it means they're going to be able to increase the size of the sequence without increasing the memory of the transformer too much, right? Which is kind of a big problem right now. Much larger feed-forward layers for the same compute, and improved parallelism during decoding. Much larger feed-forward layers for the same compute. Okay, so kind of what they're referring to here is if you're not spending all your computer memory and all your compute, right, all the time that you spend calculating the little weight multiplications and all the different little operations inside a neural net, right, the computer has to do that. That's called compute. So rather than spending all your compute multiplying these giant attention matrices that scale quadratically, they're going to be able to spend more of their compute to do larger feed-forward layers. So these layers, I guess, are probably going to be larger than similar layers in the vanilla transformer architecture. Improved parallelism during decoding. So we don't know exactly how they're going to get this, but I bet you it's going to come from the fact that these local models here can run in parallel. Unlocking better performance at reduced cost for both training and generation. Extensive experiments show that MegaByte allows byte-level models to perform competitively. Okay, so in the abstract, people want to make their paper sound as good as possible, right? So if they achieve state-of-the-art, they would for sure mention state-of-the-art. So as soon as you hear the word perform competitively, you know for a fact they did not achieve state-of-the-art with this, but they kind of got something that wasn't completely trash. So when I hear perform competitively, I hear it didn't work as good as vanilla transformers, but it wasn't completely trash. With subword models on long context language modeling, achieving state-of-the-art density estimation on ImageNet. Okay, here you go. Now they do have a state-of-the-art for density estimation. I don't know what exactly density estimation means here. And model audio from raw files. Okay, so 2 state-of-the-arts, density estimation on ImageNet, and model audio from raw files. Together, these results establish the viability of tokenization-free autoregressive sequence modeling at scale. So tokenization free, what do they mean here? Tokenization is whenever you take your text, right, such as MegaByte transformer here, this is the raw text, and you do what's called tokenization, where you take a tokenizer model, and a tokenizer model converts basically fragments of words, such as maybe byte or RAN or something like that. It cuts it up into these little word byte or word segments, and then it'll tokenize them. It'll turn them into an embedding, into a vector. And those vectors are defined in basically a vocabulary or kind of like a code book kind of situation. Tokenizer. And there's a lot of different tokenizers that people have created over the years. Let's see. Here's a nice little one. So this is what a tokenizer is kind of doing. It's taking the original sequence, which is if space test colon space function, and it's converting it into a sequence of tokens, right? So each of these things here, right, each of these squares here represents a token, and each of those is going to be a vector of the same exact size. So as far as the transformer is concerned, right, the transformer attention mechanism here, as far as the transformer attention mechanism is concerned, all of these are basically vectors of the same length, and really when it's computing the attention, as we saw here, it's not actually multiplying the word score by the word to. It's multiplying a vector that represents the token that represents this word here, or this part of the word here. So having to tokenize before feeding something into a transformer is sometimes annoying, and you're also in a way limiting yourself to whatever that tokenizer, whatever kind of embedding space that tokenizer is limited to, right? We don't know if the tokenizers we use are perfect, and we don't know if there's better tokenizers that we could be using. So maybe if you get rid of this tokenization step, you can unlock better performance. And then auto-regressive here. Regress just means basically kind of like produce something, right? For example, you can use a neural net to do regression, at which point the neural net is directly predicting a value, and then auto-regressive just means kind of doing that to yourself. So auto-regressive, there's a lot of different things that could mean. Sometimes it means kind of like an RNN or something like that, where the network is looking at its own output, but I don't think that's what it's doing here. It's probably just going to be paying attention to a slightly, maybe the local model pays attention to the previous local model or something like that. I'm not sure. But I'm sure that by the time we read this paper, we will understand what they mean. All right, introduction. Sequences of millions of bytes are ubiquitous. For example, music, image, or video files typically consist of multiple megabytes. Okay, so here they're referring to the fact that 1 megabyte is a million bytes. Right, I think it's actually a million bits. 1 megabyte is 1 million bits. No, 1 megabyte is 1 million bytes. Yeah, I mean, of course, that makes so much. It literally has the word byte in it. Okay. So they're basically saying, hey, you look at images. Images might be a couple megabytes. Songs might be a couple megabytes. Therefore, there's plenty of different types of data in the real world that are roughly this size, right? 1 million bytes. However, large transformer decoders typically only use several thousand tokens of context. So we saw that in one of the previous papers we were looking at. I think GPT has a context of 8,000 tokens. There's famously the Anthropic model, I think it's called Claude, which has 100K tokens of context. And people are kind of fighting to have the biggest, baddest context, but they're all kind of using the same vanilla attention mechanism, so they're kind of running into the same issues. Both because of the quadratic cost of self-attention, but also more importantly, the cost of large feed-forward networks per position. Yeah, so you have the memory cost, and then you have the actual compute that you're spending every time you perform the inference. This severely limits the task where LLMs can be applied. We introduced MegaByte, a new approach to modeling long byte sequences. First, byte sequences are segmented into fixed size patches, loosely analogous to tokens. Okay, so they're going to cut the actual sequence here, so such as the word MegaByte transformer, and they're going to cut it into these little, what they're going to call patches. So this is reminiscent of what you do in a vision transformer, where you take an image and you cut it into patches. So maybe inspired by vision transformers. Our model then consists of three parts. One, a patch embedder. Okay, that's very similar to kind of a tokenizer. Which simply encodes a patch by losslessly concatenating embeddings of each byte. Okay, so each byte is encoded, or is embedded, right, turned into a little vector, and then they encode the entire patch by just concatenating each of those. Okay, so each of the letters inside the individual patch is going to get turned into an embedding, and then they're going to concatenate those 4 embeddings. I don't know if the actual number is going to be 4, but we'll see. A global module, so the second part of this, is a large autoregressive transformer that inputs and outputs patch representations. So this is this part right here. Right, and you see how the patch, I guess actually it goes this way. So the input is this, and then this is the output. So you have your patch embedding. Each of those gets fed into the global model. So each patch embedding here is only looking at a limited limited window, right? It's only looking at its own little individual patch. And then the global model has can look at all the patch embeddings. A local module, a small autoregressive model that predicts bytes within a patch. Global out. And then that, you see here, this little plus means concatenation. So the global out is concatenated with, it almost looks like it's basically just the next patch. And then you have a little local model here that's looking at this, which is basically the next part of the patch, plus concatenated with the output of the global model, and then it does some kind of attention mechanism here, and then outputs the next one. So you see how it's receiving this information, which is basically the beginning of the sequence. That's going into the global model. The global model is giving it some kind of embedding here, which should represent the entire sentence, the entire sequence. That's being concatenated with everything up into here, so basically kind of the next 3 things. And then it's predicting, the local model is really just predicting the last thing. You see how it's already received _MEG, so really the only thing it's predicting here is the next token. Even though here it's not tokens, it's patch embeddings. How's the paper so far? It looks interesting. But I'm kind of just getting a little distracted, so I haven't even gotten to the meat yet. In Karpathy's tweet, he said, tokenization is why GPTs are bad at number or very simple spelling character manipulation tasks. Really resonated with me. Yeah, so I think tokenization is definitely limiting current transformers, because the tokenization is kind of fixed, right? And you're assuming that the embedding space that the tokenizer is putting all these tokens in is really good, but I don't think it is. I think it's quite poor, probably, right? Like, what is the most popular tokenizer? What is the most popular tokenizer? The most popular tokenizer is WordPiece. It's a subword tokenizer developed for use with BERT. Can handle out-of-vocabulary words, breaking them down into subwords. All right, what was this tokenizer? What was that tokenizer trained on, in terms of data? We observed that for many tasks, most byte predictions are relatively easy, for example, completing a word given the first few characters, meaning that large networks per byte are unnecessary, and a much smaller model can be used for intra-patch modeling. Okay, so they're basically referring to the fact that if you are just predicting the next byte here, right, this letter A, you don't really need the entire global context to do that. You just need this little local context. The word piece tokenizer was trained with a massive dataset of text and code. The dataset includes text from a variety of sources, blah, blah, blah. Yeah, algorithm starts with a vocabulary of individual characters, then iteratively merges. So, okay, TLDR basically is that the tokenizers are limited to whatever dataset they're trained on, right? So you can keep making a bigger and bigger and bigger transformer and train it for longer and longer and longer, but at some point, the weakest link in your chain is not going to be your transformer or the dataset that you're training your transformer on. The weakest link in your chain is actually going to be the tokenizer, because the tokenizer isn't going to the embedding space of the tokenizer isn't really going to fully represent the true dataset distribution of all human text, right? So I do think maybe we're getting to the point where the tokenizers are actually limiting the progress. But that's not 100% guaranteed. That's just me kind of talking off the cuff there. The MegaByte architecture gives three major improvements over transformers for long sequence modeling. Subquadratic self-attention. Most work on long sequence models has focused on mitigating the quadratic cost of self-attention. MegaByte decomposes long sequences into two shorter sequences, and optimal patch sizes reduces the self-attention cost to O(n) to the 4/3. So this is big O notation. So this is if you guys have ever done leak codes, or if you've ever kind of applied to big tech companies for programming positions, you'll be familiar with this. But basically, any kind of computational algorithm has a complexity associated with it, right? You can have a complexity with regard to the time it takes, and a complexity with regard to the memory it takes. So what they're referring to here is that this function tells you the kind of scaling of the self-attention cost here, right? So as you increase the size of the memory, or the size of the sequence, n roughly represents the size of the sequence, the computational memory cost of the self-attention mechanism normally would be n squared, but in this paper it's subquadratic, so you see how it's n to the 4/3. Per patch feed-forward layers. In GPT-3 size models, more than 98% of flops are used in computing point-wise feed-forward, position-wise feed-forward layers. MegaByte uses a large feed-forward layers per patch rather than per position, enabling much larger and more expressive models for the same cost. Okay, so position-wise feed-forward layers. I think position-wise here, they're referring to the position within the sequence, right? And the position encoders. And somehow those are basically using up all the compute, and then in this paper they're using the compute on more expressive model. There's no like formal definition for this, like more expressive model, like that's not like a real scientific term there. That's just kind of like a subjective opinion. With patch size p, finally getting our first little math definition there, where a baseline transformer would use the same feed-forward layer with m parameter p times. MegaByte can use a layer with mp parameters once. Okay, this is kind of interesting. These might be shared, this local model. If they're shared, then it would make sense because that's what they're talking about here with the parallelism, but we don't know. They haven't said that explicitly, so let's see. Parallelism in decoding. Transformers must perform all computations serially during generation. Serially just means one at a time, right? Because the input to each time step is the output from the previous time step. Yeah, the transformers run on every single token, right? So every time you, whenever here this transformer that is behind the barred right? It has this is the sequence, and then it produces this token. And then it has this is the sequence, and then it produces this token. And then it has this is the sequence, and it produces that token. So literally every time it creates a token, it runs a full inference step with everything previous. So that's why GPT is very slow, for example, GPT-4, when you go on it. It's because it's literally performing an inference step for every single token that you create. So if I say, I don't know, write me a song about tokenizers, right? You see every little what it's scrolling through here is basically tokens. So actually every time a word appears, that is one token. So you can actually kind of tell whenever the token is the whole word or whenever the token is a part of a word. So inference, 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 inference. That's how many times it's doing inference, which is quite a lot. Together, these improvements allow us to train much larger and better performing models for the same compute budget, scale to very long sequences, and improve generation speed during deployment. Potentially huge. MegaByte also provides strong contrast to existing autoregressive models that typically use some form of tokenization, where the sequences of bytes are mapped to larger discrete tokens. Yeah, so this is kind of what we've been talking about, where tokenization complicates preprocessing multimodal modeling. This is because you can't use a tokenizer for text for images, right? Images and text are going to use different tokenizers. Tokenization in image space is actually not, it's a completely different thing, but you can't use the same tokenizer that you would use for a sentence and text that you would use for audio, right? So transfer to new domains, again, your tokenizer is kind of frozen, so whatever you trained it on, it's kind of frozen for that specific thing. So if you wanted to use, if you wanted to tokenize a text in a new language, you wouldn't be able to really use the tokenizer from before, especially if your tokenizer doesn't have characters or symbols that are in the new language. Hiding useful structure from the model, right? They're kind of limited to whatever embedding space the tokenizer ended up creating. It also means that most state-of-the-art models are not truly end-to-end, right? They're using a frozen pre-trained tokenizer. The most widely used approaches to tokenization require language-specific heuristics or lose information. Replacing tokenization with efficient and performant byte models would therefore have many advantages. We conduct extensive experiments for both MegaByte and strong baselines. We use a fixed compute and data budget across all models to focus our comparisons solely on the model architecture rather than training resources. Okay, so obviously they don't necessarily just want to, they do want to push the boundaries, and if they could train a model that was state-of-the-art, they would have definitely done that. But what they really wanted to do was compare this particular model architecture, right, this MegaByte model architecture, to the GPT kind of quadratic self-attention architecture with a tokenizer. So what they're going to be doing is they're going to say, okay, well, we're going to use the same amount of compute and probably a smaller data set and see what the difference is, right? So this is kind of a paper where you're trying to compare to a specific other approach rather than trying to necessarily push the boundaries, which is usually what people do when they have limited budgets, right? If you're just inside a research group, you don't have infinite budget. You can't spend $100 million to train a MegaByte without knowing if it's going to be good or not. So you train a smaller version of it with a smaller amount of time on a smaller data set and then see how it compares. We find that MegaByte allows byte-level models to perform competitively with subword models on long context language modeling, achieve state-of-the-art perplexity. So perplexity is a measure, kind of a quantitative measure for text. For density estimation on ImageNet, and allow audio modeling from raw audio files. So they do it on a variety of different modalities here. They're doing it on text, they're doing it on images, and they're doing it on audio, which makes sense, right? Because because they don't have the tokenizer, they can do it on, they can use the same model architecture on a variety of different modalities, which means that of course you bet that they're going to be doing that, right? Because they want to showcase that they can do that. This actually really reminds me of the DeepMind Gato paper, if you guys have ever heard of this. So this was a reinforcement learning paper. It's a little bit older at this point, but this paper was very interesting because it did not it wasn't limited to a specific modality. It basically, any input sequence worked, right? So here they showed you with robots, with any kind of game, with Mujoko simulations. This agent was basically able to perform reinforcement learning on pretty much anything, right? A prompt is tokenized, forming an initial sequence. So I guess in this particular paper, they had a tokenizer which tokenizes any input modality into the same embedding space. I forget exactly how they did that. But it's the same kind of idea, right? Where it's like, hey, let's feed in all these different modalities as if they were sequences from the same underlying distribution. MegaByte transformer. MegaByte is an autoregressive model for efficiently modeling long input sequences. MegaByte is comprised of three components: a patch embedder that inputs a discrete sequence, embeds each element, and chunks it into patches of length p. So this is really this is a tokenizer. They're calling it a patch embedder, but this is what a tokenizer is doing in a vanilla transformer. It's taking the individual little words and chunks of words and turning them into embeddings or vectors that have a very specific consistent length. So they're calling it a patch embedder here, but like really it's just a tokenizer that's built into the architecture. A large global transformer that contextualizes patch representations by performing self-attention over previous patches. So this seems like your kind of standard transformer self-attention mechanism there. And then a smaller local transformer that inputs a contextualized patch representation from the global model and autoregressively predicts the next patch. So the autoregressive part here refers to the fact that it has it's using both the output of the model concatenated with the actual sequence itself. So it's like looking at its own output is kind of a way to think about that. All right, patch embedding. With the patch size of p, maps a byte sequence x naught t to a sequence of patch embeddings of length k, t over p, and dimension p times dg. Okay, so you have a sequence of bytes of length t. You have the size of the patch embeddings, right? The size of the vectors, right? The size of this thing here, this patch embedding, right? This little vector here represented by this square is of size t over p, which is interesting. The size of the patch embeddings is a function of the patch size and the length of the sequence. And then dimension p and dg. We don't know what dg is. What is dg? dg is embedding size, so the size of the embeddings, and positional embeddings. Each byte is embedded with a lookup table. Lookup table sounds very, very similar to a tokenizer. So tokenizers have a limited vocabulary, right? So tokenizers are taking word chunks and turning them into tokens, but those tokens aren't continuous. They're usually within a specific vocabulary, right? So how many tokens, or what is the vocabulary size for the word piece tokenizer? I think it's like 40,000 is a number that I'm thinking about. 30,000. Yeah, so the tokenizer used in WordPiece and BERT, which is probably the tokenizer that's being used right here inside this BARD model that I'm talking to right now, there's only 30,000 possible words or 30,000 possible tokens, right? So it has a limited vocabulary. And as soon as I see the word here, lookup table, that to me screams limited vocabulary size. So I don't know, that seems a little sketchy to me, but that size is E global embed is the size of that, I guess, and the dimensionality of that is V cross DG, where we don't know what V is yet. They haven't defined that. I guess V is probably the size of the vocabulary. So this is the size of the embedding, and then V is the size of the vocabulary. And then you have embedding size and positional embedding. So positional embeddings, this is kind of a whole rabbit hole, but there's a very good blog post that I remember. Maybe it's this. Yeah, so what a positional embeddings is doing is it's basically giving the neural net a little embedding vector that allows the neural net to understand at what point position in the sequence this token is, right? So every token in your sequence has a certain position relative to every other token in the sequence, right? And you want to be able to say, basically the model needs to know this is the first word, this is the 10th word, this is the 500th word, right? But you don't just want to pass in literally the number 0 and 10 and 500. You want to pass in a number that is bounded and nice and kind of well shaped, right? Like in anytime you're doing numbers inside of neural net, you want to make sure they're in between, for example, -1 and 1, right? Or 0 and 1 or something like that, right? You want them to be very normalized, right? So positional embeddings is basically this way of representing the position of things inside of a longer sequence of things such that it's always a number between -1 and 1, and they do that basically with these sines and cosines. So that's how tokenization works, or positional encodings. And there's different ways of doing positional encodings, but that's like a whole rabbit hole. So we'll just think of it as basically a little embedding vector that lets the neural network know where within the sequence this particular token is from. So let's actually take this because I realize I'm going to continue to keep scrolling up and down. So I'm going to just do this so I can very easily scroll up and down. Okay. So HT embed, which is here, right? H embedding is equal to E global embed. So the output of the global model, and then the positional embedding, and there's T of these. So they don't show the positional embedding here, but I bet you it's coming in either right here or right here. Byte embeddings are reshaped into a sequence of k patch embeddings with dimension p times dg. To allow autoregressive modeling, the patch sequence is padded to start with a trainable patch size padding embedding. So the patch sequence is padded. What are they referring to? They're referring to the fact that here you see how this is empty. That's padding, starting off with empty. It's probably 256 vocab size if it's just a lookup table over all possible bytes. Yeah, I think so. I think the lookup table might be over all patch embeddings, but I'm not sure. No, you're right. Each byte is embedded with a lookup table. So the lookup table is specific for the byte, which means that, yeah, each byte is going to be one of 256 possible values. I think you're right, Oizen. To start with a trainable patch size embedding, or patch size padding embedding, and the last patch is removed from the input. This sequence is the input to the global model and is denoted H global in. Okay, so H global in, this right here, this little vector here, or this embedding here, H global in, right here, H global in, and then the underscore here, K, refers to the fact that there's K of these, right? So here K equals, I guess, 4, but K is going to be much larger in the actual thing, or in the actual model. So if K equals 0, right, so in the first one, E global pad, it's going to be the padding, so this is going to be the empty, right? Empty bytes, 4 empty bytes and then you end up getting what they're calling the E global pad. And then for every one after that, so this one, and this one, you have this H embedding, which is a combination of the global embed plus the tokenizer, or not the tokenizer, the position encoding. And that goes from k equals 1 to k. What the fuck is this part right here? K minus 1 times p to k times p. So if k equals 1, then k minus 1 is 0. 0 times p is 0. So it would be 0 to p. Okay. So really, I guess they're just saying it's every p, chunks of size p is basically what this part down. This subscript here is just letting you know that this embedding vector here, this h embed, is relative to chunks of size p. The global model is a decoder-only transformer with dimension p. DG that operates on a sequence of k patches. So decoder only, I think we were looking at this before, and it was I found a nice picture for this, decoder encoder transformer. Yep, here we go. Yeah, so at a high level, what is encoding and decoding? So at a high level, encoding is taking inputs that are higher dimensional and encoding them into a lower dimensional embedding or vector representation, right? You're basically compressing information. Decoder is uncompressing information, right? So that's what encoders and decoders are at a high level. But transformers normally have an encoder block and then decoder blocks, and then they have n amounts of these blocks. So whenever they say decoder only transformer, they're basically saying that you don't have this part here. It's just decoding only. So it's only this part here. See if we can find a better picture. Yeah. So the next input to the decoder will be SOS bonjour. We may get bonjour le as the input. So you see how the decoder is receiving its own output. So it's auto-regressing on that. Boom. And you see here the positional encoding that's coming in. And this little weird symbol here, like, what does this mean? If you actually look at it, it's a cosine and a sine function, right? Cosine and sine functions are these like little waves. So that's what this little circle with that little wave, it's not like a yin-yang symbol, it's a cosine inside a circle. And this little circle with a plus in it means concatenate. So they're taking the embedding here, which is just a vector, and they're concatenating it with the positional encoding, which is also a vector. And in order to concatenate, these two vectors need to be the same size. Okay, so the global model is a decoder-only transformer with dimension PDG that operates on a sequence of k patches. So there is k patches here that the global model is getting. And each patch is of size p times dg. Oh my god. It incorporates a self-attention mechanism and causal masking to capture dependencies between patches. So causal masking here, masking is whenever you mask out certain parts of the attention mechanism. So you see here, none of the attention mechanism here is masked, right? If it was masked, then you would basically see a bunch of zeros. And one common form of masking is masking everything ahead of the word. So, for example, in a masked self-attention mechanism, you would basically see resources would have some value with it, some value with this, some value with this, but then as soon as you get to this value here, every value after this would be 0, right? It would be masked out. So if you ever see a transformer attention map where basically the whole top part of it like this is zeroed out, that's telling you it's masked. Masked attention mechanism. Yeah, here you go. So this is what masked attention would look like. Where's that picture? I literally just saw it. This one? No. There we go. Boom. Masking the self-attention to ensure that elements can only attend to the input element that precede them. So this is a very common form of masking, where basically you mask out anything that is beyond. So the first character in the sequence, the first token in the sequence, the first patch embedding in the sequence can only pay attention to the first patch embedding in the sequence. It cannot pay attention to any of the other future embeddings or tokens or words. So here they're doing a different type of masking, causal masking, to capture dependencies between patches. It inputs a sequence of k patch representations and outputs an updated representation by performing self-attention over previous patches. So over previous patches makes me think that it's doing this kind of masking based on the sequence, but we'll see. Okay, so the global model here, it's taking in this h global in and outputting h global out. So h global in, and there's 0 to k of those h global ins, and then h global out, it's also 0 to k. So the dimensionality of the input and the output for this global model is the same. It's outputting k embeddings. Transformer global h0k global in, and it gives you h0k global out. Okay, that makes a bunch of sense. Global layer contains k patch representations of dimension p times dg. For each of these, we reshape them into sequences of length p and dimension dg. Okay, so they're going to take the output of this global model and reshape it back into a sequence, right? Where position p uses dimensions p times dg to p plus 1. Each position is then projected onto the dimension of the local model with a matrix WGL equals dg cross dl, where dl is the local model dimension. Okay, so basically they need to reshape what comes out of this global model, right? This individual patch, of which there are k, and they need to reshape it such that this local model can consume it. And that's why they're they call it mapping here, projected, but that just basically means either a linear layer or basically just taking that vector and then just like cutting the pieces up and moving them. I think they're just reshaping. So reshaping doesn't change the values of anything. It basically just moves the existing values around, versus projecting usually refers to the fact that you're feeding it, you're doing like one basically feed forward. So it's not entirely clear to me which one they're doing, because they use the word reshape here and then they use the word projected here. We then combine these with byte embeddings of size DL for the tokens in the next patch. Byte embeddings for the tokens in the next patch, so that's this part here. So they're combining this global model here. You see this little plus, the concatenation, and they're concatenating it with the byte embeddings here. So they're actually, and it's not actually even the next patch. It's, yeah, you see, it's not exactly the next patch. It's the next patch minus 1. So you see, they're not giving it MEGA, they're giving it underscore MEG, and then what the local model's supposed to predict is supposed to predict A. So really, they're basically doing next token prediction, but at a much smaller local scale. And the little local scale, the little local model that is doing this little tiny next token prediction, even though it's not next token, it's actually next byte. This little local model that's doing the next byte prediction, it receives this vector here, this h global out, that supposedly has information about the entire sequence, right? So the global model is the only one that sees the entire sequence. But this little local model, it's only able to access, quote unquote, the whole sequence by uh, the information that is passed into it through this H global out here, which is a little interesting. The local byte embedding is offset by 1 with a trainable local patch embedding. Yeah, so offset by 1 here, just the fact that it's getting underscore MEG, not MEGA. E local pad has the same dimension, DL. Summary of MegaByte with vocabulary V. Okay, so V was the size of the vocabulary. Sequence length T. Global, local, and global and local dimensions DG and DL. So DG stands for dglobal and DL. So dimensionality of the global embedding and the dimensionality of the local embedding. So this and this I get are different dimensions. Yeah, that's probably why it's a dotted line here versus a solid line here. And K patches of size T, or K patches of size P, where the patches are these things here, right? You get the patch, you embed it into this vector. Transformers use mask self-attention to not observe information from future time steps. Okay, so they are doing this. They are doing this masked attention where you only pay attention to the things that are either at your position in the sequence or before your position in the sequence. You don't get to you don't get to see, or no information comes into the comes in from previous or things that are in the future of the sequence. Damn, I'm like just twisting my words today, but okay, that's kind of what we were expecting with the masked, but it sounded like they were maybe doing a little bit more fancy kind of masking, but it's basically just the same generic masking. Okay, so basically, what is this? We got all the different math that they put inside these paragraphs, but I guess now they just have them all sitting out here. So we have HT embed, which is HT embed is this, is EXT global embedding, and then ET positional embedding. So this is of dimensionality global times however much your vocabulary is. And our guess is that the vocabulary is 256. H global in, E global pad, right? So if you're in the very first patch that gets fed in is basically always the same. It's this empty padded sequence here, which they call E global pad. For everything else after that, it's H embed of size P, right? So initially your vectors or your bytes are within 0 to 256, right? This vocabulary size, but then they become of size P. H global out. This is your global transformer right here, your global model, which is just a transformer, which is masked. The dimensionality of global out is K cross P times DG. The dimensionality of global in is K cross P times DG. So those are the same. Global out, global in, same dimensionality. H local in and local out. These are different. See that? H local in is of size DL, but H local out is of size K cross P times DL. So this local model here, different input size than output size. What is WGL? W is probably just the weights of the transformer. Did they define this W? Did we read that? Yeah, here we go. Boom. All right, never mind. We did read it. Each position is then projected to the dimension of the local model with a matrix WGL. Okay, so the WGL is what's projecting from the global out into the local in. So in between the global out and the local in, they have to change the dimensionality of this global out. They have to project it into a dimensionality that can be fed into this local in. And they're projecting it in such a way that they're probably also adding the positional encodings. No, the positional encodings are all the way at the beginning, my bad. Okay, so they need to change this H global out, which is this K cross P times G, into H local in, which is DL, right? So the weight matrix here, WGL, is going to be that. DG cross DL, K cross P times DG, DL. So if you go from this times this equals this. Dude, these are so confusing. All right. Then what happens? Then you take this local out, which is right here, and you convert it back into the vocabulary, right? Because right now you don't have actual vocabulary tokens. You have basically just these embeddings. And they take the softmax of those, which is basically the output here is going to be a size of the vocabulary and then a probability for each of those. So when you're doing a text large language model, at every single, so like let's say you're here, right? This is your prompt and it's now trying to perform one step of inference and give you the next token. What the model is actually outputting, it's not outputting that token directly. What it's outputting is basically however many 30,000 tokens, and it's a probability for each of those 30,000 tokens. And then you're saying, okay, this is the probability that the next token is each of these 30,000 things. And I'm going to pick the one that has the highest probability. So the same thing is happening here, right? Where you take the final thing and you're like, okay, and then out of all of these, I'm going to put the softmax through them and then get the argmax of those. And that should give you the final byte. Or at least the final position within the lookup table that contains all the bytes. Right? So the final output of this little number right here, you'll be able to take that little number right there, go to your lookup table, and say that number, according to this lookup table, corresponds to this byte, which will be some Unicode character probably. This results in a tensor WGLH. The local model is probably run 4 times. So in the top right section of the diagram, if first you run the local model to get S, then F, then O. Yeah, and I think the whole point is that this local model is probably going to be the same. That's my guess, is that part of the reason they're doing this is that each of these local models is going to be the same, which means that they're going to be able to run these in a GPU in parallel, right? And then also here on the input, right, you can run in parallel. So it seems to me like that's kind of one of the bigger reasons they're doing this. It's like, why are they cutting it up into these patches, and then when they're doing the decoding, they're cutting it up with these little local models too. It's like, what's the whole point of doing that? I think the whole point of doing that is so that you can basically do all of these steps in parallel. So it's a lot faster too. In addition to having a very long, or being able to adapt to a very long input sequence, it's also kind of inherently easy to parallelize. Local model is a small decoder-only transformer of dimension dl that operates on a single patch k. Single patch k containing p elements, each of which is the sum of an output from the global model and an embedding of the previous byte in the sequence. So what they're saying here is that the local model receives the embedding from the global model, right, this global out, and it's also receiving the previous byte in the sequence, which is underscore MEG in this example. K copies of the local model are run on each patch independently. So you kind of have like similar to multiple heads, you have multiple of these local models and in parallel. So there you go, boom. That's the whole point. Computing a representation H local out K cross P times DL here. Finally, we can compute the probability distribution over the vocabulary at each position. So this is kind of what I was trying to describe, but in slightly shittier words, is that at the end of the day, this local transformer is going to give you a probability distribution over all the different bytes in your vocabulary, right, in your lookup table, and you're going to pick the one that has the highest probability. The pth element of the kth patch corresponds to element t of the complete sequence. So here what they're referring to is that the output of this local model, you already know what MEG is, right? So you don't actually need this MEG. What you're really interested in is this last character here, what they're calling the pth element, right? So this A, this E, this N, this R. And ultimately, here you go. What you really want is the probability of the t byte given all the bytes up until that, right? And here the x from 0 to t, that's telling you all about this mask here, right? Because you're not using the stuff ahead of you. And why don't you use the words in front of you, right? Right? You could look at this and say, well, that doesn't make any sense. Like, why would you not use the information ahead of you in order to better understand the sequence? And the reason is that when you actually run these things, you don't know what the word ahead of you is, right? So when Bard is taking my input and then adding to it, it only knows everything up until here, right? It's like in order to predict this word here, this used, it's only using everything up until that point. And then in order to predict the word in, it's using only everything up until that point, right? So really what you want is a probability over all of the vocabulary tokens conditioned on every previous token in the sequence. And the softmax here just basically turns it into the one that has the highest probability. We experiment with several extensions of MegaByte. Okay, so it seems like they're going to have a couple different ablations here. They're going to try to do a couple different things and see which one works the best. One limitation of chunking sequences into patches is that it is not translation invariant. And byte sequences may receive a different representation depending on their position in the patch. Translation invariant. So what are they referring to here? So translation invariant means that if I took this exact sentence and I added a letter beforehand, let's call it, let's say the MegaByte transformer, then all of these would change, right? As soon as I translate the sequence, like translate here, not referring to the fact, not referring to like translating from English to French, but translating along kind of the X dimension, right? The dimension of the sequence. Sequences only have one dimension that is like basically forward in time. So this mechanism here, because you're cutting it up into these little patches, it's not translation invariant. It's going to change if you move the sequence. And you might get different combinations, right? You might, rather than getting the byte M, E, G, and A, you might end up getting the bytes GABY, right? So that could potentially be an issue. And byte sequences may receive a different representation depending on their position in the patch. This may, for example, mean that a model has to relearn the meaning of the word with different offsets, which could be huge. To mitigate this issue, we experimented with augmenting the patch embedder with causal convolution layers, which allow translation invariant contextual representations on the bytes before they are chunked into patches. We use a stack of convolutional layers with filter sizes of 3, 5, and 7. Okay, so we experimented with augmenting the patch embedder with causal convolution layers. Okay, so what are they saying here? They're basically saying that right now, the patch embedding model is only looking at the stuff kind of immediately within the same, like immediately the next 4 things, right? So here they have p equals 4, so you're splitting up your sequence into these patches of 4, and then you're feeding those 4 directly into the patch embedding, but the patch embedding has no idea what's before or what's after. It's only getting that limited little context window. So it sounds like what they're describing here is that you're going to be doing a convolution. So rather than the patch embedding only seeing these 4 things, it's going to basically get a convolved version of a larger part of the sequence, right? So receptive field convolution. Let's get a good picture of this. Yeah, this is the picture that I like to show for this, where by using convolution, you can basically get a larger amount of the total sequence or total input to be like visible is the word to use to each individual thing. So with convolutions, in this case, they're not talking about 2D convolutions, they're talking about 1D convolutions, specifically with sizes 3, 5, and 7, right? The filter is the size of the little square that you're using to convolve. So you see here, this is a 3x3 filter. Here they're talking about filters of 3, 5, and 7, and 3, 5, and 7 there refer to the size or the number of these bytes. So they're going to be convolving across probably just a part of the sequence with that convolution of those different size filters, and that will allow the patch embedding to have at least a mechanism by which it can kind of pay attention to some of the other parts or use some of the other parts of the sequence. So that's one thing they're trying. All right, a different thing that they're going to try is their cross-patch attention. The local model uses short sequences for efficiency and relies on the global model for long-range information. However, we can increase the context of the local model with little overhead by allowing it to condition on R elements from the previous patch. This approach allows the global model to focus on a longer range context. Increase the context of the local model by allowing it to condition on R elements from the previous patch. So right here, this local model, right, it's conditioned on the output of the global model and then the encoded previous patch, right? So it's not really the previous patch. It's right here. It's just kind of the next patch almost. It's like the next patch -1. But they're saying, okay, well, what if we also give it access to previous patches? So what if this one here, the local model, it received the global embedding, then it also received this _tran, and then it also received maybe a bunch of extra stuff. Maybe it also received mega and then this part here. So giving the local model elements from previous patches. This approach allows the global model to focus on a longer range context. This is more kind of just black box explanation. They're saying that, hey, if you pass explicitly information from previous patches into the local model, maybe that makes it so that the global model doesn't have to worry about putting a ton of kind of medium scale information here, and the global model can just focus on putting very, very long scale things in there. When computing self-attention in each layer, we concatenate the keys and values with the last R keys and queries from the previous patch. So keys, values, and queries are different parts of the attention mechanism, and here the attention mechanism is happening inside the global model. We use rotary embedding, so this is a different type of positional embedding, to model relative positions between embedded elements in the sequence. Right, so any kind of position embedding is basically ultimately telling the model where within the sequence that embedding or that specific part of the sequence exists. This approach is reminiscent of Transformers XL, but differs by being fully differentiable. Okay, so why is fully differentiable important? Anytime you're doing a machine learning approach, you're using basically gradient descent in order to improve or optimize variables and over time basically push them in the direction that you want. In order to do that, you're going to need to do backpropagation. In order to do backpropagation, you're going to need to calculate the chain rule. In order to do the chain rule, you need everything to be differentiable. So that's why being fully differentiable is important, because it allows you to do the chain rule, which allows you to do backprop, which allows you to learn the values of different parameters. Strided inference. We observed empirically that per token loss within each patch, I like how they're literally talking or calling it token, within each patch would increase towards the end of the patch, as the prediction relies more on the weaker local model. To alleviate this issue, we propose strided inference, in which we predict the sequence with 2 forward passes of the full model, whose inputs are offset by p/2 positions from each other. Okay, so they're going to run the model twice, and then they're basically going to run the model twice, but first time they're going to run it with basically just like this, and then the second time they're going to run it, but they're also going to offset it, right? So it seems like a lot of the techniques they were describing here have to do with the fact that it's not translation invariant. So you see, these are different ways of dealing with the fact that it's not translation invariant. Either you do this convolution type of approach, which increases kind of the receptive field and allows the patch embedding to pay attention to different part. I hate using the word pay attention because attention means something, but it allows the position embed or not the patch embedder to look at different parts of the sequence. That's what this convolution is doing. And the strided inference is kind of trying to do a similar type thing where it's trying to solve this problem of the invariance by, in this case, shifting the sequence. So it shifts the sequence and then it runs this whole model twice. Similar to sliding window techniques, this approach doubles the cost of inference. That's the problem. Having described the model, we briefly discuss the motivations behind some of the architectural choices. Why is the local model needed? Many of the efficiency advantages of MegaByte design could be realized with a global model alone, which would resemble a decoder version of the VIT. Yeah, this is kind of, I mentioned this at the beginning, right? The patches just, to me, just screams Vision Transformer. And the Vision Transformer is doing this exact same thing. It's turning an image into patches and then feeding in each of those patches. Right? You see this? It's taking the image, it's cutting it into these little patches, and then feeding each of those patches into a transformer, a larger transformer, which is what's happening here, right? It's you're cutting the sequence into these little patches. And it always seemed very arbitrary to me about the size of the patches, and like it just never seemed super good, but that's kind of what they're doing here as well. However, the joint distribution over the patch, pxt plus 1 all the way to all the way to xt plus p from given x 0 to t, right? So you're conditioning on all the bytes from 0 to t, and then you're trying to predict the probability of the next byte, and then all the bytes up until p. Has an output space of size 256 to the p, so directly modeling is only tractable for very small patches. Okay, so the size of the patch is determined, or at least limited by, the fact that your distribution and the joint distribution because you have multiple parts of that patch that you're trying to predict. We can instead factor this joint distribution into conditionally independent distributions. Okay, so they're going to take this distribution here and split it up into two distributions. Right, so the probability of A comma B given C is the same as the probability of A given C times the probability of B given C. So it's kind of just like pulling those two out. I don't, conditionally independent, I don't, like, is that independent? I don't know. But this would greatly limit the model's expressive power. It would be unable to express a patch distribution such as 50% cat and 50% dog, and would instead have to assign probabilities masked to strings such as cag and dot. So they're saying if the probability distribution is over individual tokens, right? If you're or not individual tokens, but you're only predicting individual bytes, then you might have nonsense, right? Such as cag and dot because you're predicting individual bytes. But they really want a probability distribution for the entire kind of patch. Is that kind of what I'm getting? Instead, our autoregressive local model conditions on previous characters within the patch, allowing it to only assign probability to the desired strings. Maybe? I don't know. This is definitely kind of confusing me here. I don't really understand. Increasing parameter for fixed compute. Transformer models have shown consistent improvements with parameter counts. However, the size of the model is limited by the increasing computational cost. MegaByte allows larger models for the same cost, both by making self-attention subquadratic and by using large feed-forward layers across patches rather than individual tokens. Yeah, I think this is the big one here. These local models can be run in parallel. That's the big one. Reuse of established components consists of two transformer models interleaved with shifting, reshaping, and a linear projection. This reuse increases the likelihood that the architecture will inherit the desirable scaling properties of transformers. Okay, so what they mean here by scaling properties of transformers is, of course, the power law scaling that everybody refers to, where there's this nice little property of transformers where if you keep making them bigger, they seem to work better. And here they're saying, hey, by only using things that exist already, like a transformer here, embeddings, a little local model, like we're not introducing anything weird, so therefore we should expect this model architecture to also continue to scale. We analyze the cost of different architectures when scaling both the sequence length and the size of the models. The cost of self-attention in a transformer architecture for a sequence of length t has O of t squared, so big O notation t squared, right? As you increase the size of the token or of the sequence, the complexity or memory increases by the square of that. Much work has been explored reducing this. For example, sparse transformers and routing transformers show strong results with complexity O of t to the 3 over 2. So sparse transformers, I think, is whenever you're not basically doing the full attention mechanism. Your sparsity is coming in here, basically. Let's see, sparse transformers. See if we can get a nice pick. Yeah, look at this. Sparse attention methods. So you see all these different clever types of masking and looking at the attention block. Here you go, routing attention. So that's probably the one they're referring to here. This routing transformers. local attention, variable sparsity attention. It's just all different ways of taking that big square of numbers and breaking it up into more doable things. Performers. Numerous linear attention mechanisms have also been proposed, although we are not aware of competitive results on large language modeling tasks. A function of sequence length t and patch size p, the global model has a sequence length of p over t. Right? You're breaking up the original sequence of size that has a length t and then breaking it up into patches of size p, so the global model here is effectively looking at a sequence of length p over t. So it uses O of t squared over p squared. That's the complexity of the attention mechanism in the global model. The local model uses p over t sequences of length p, so the complexity of the local model is O of t p squared over p, which simplifies to O of pt. This is complexity in terms of total amount of operations required. This here is complexity in terms of memory. So big O notation can be used to specify the complexity of the memory. There's memory complexity, and then there's also time complexity. So these are, when they have the word operations here, that refers to the time. The overall cost in megabytes is therefore this. All right, so obviously you're doing this and then you're doing these local models, so the total cost is that. And generally, when you're doing the big O notation, you get rid of that. So let's say your big O notation complexity was n squared plus n, you would just say O of n squared. So the big O notation, you basically get rid of the terms that are not as big as the biggest term. So here, the dominant term here is the t squared over p squared. P is a hyperparameter that is chosen to create an architecture for sequences of size t. By setting p equals t to the 1/3, the complexity is in O t to the 4/3. Okay. So they set the patch equal to the cubic root of the length of the sequence, which means that they can plug that into the big O notation here and simplify it out, and you end up getting this as the total complexity, which is smaller than t squared. Using much shorter patches would give complexity of O t 8 to the 5th. The cost is less than the transformer for all non-trivial values such that 1 to p to t. Okay, so they're saying no matter what you pick for the size of the patch, as long as it's less than the size of the sequence, then you're getting some benefit in terms of the computational complexity, which makes sense, right? If you cut up the sequence into smaller pieces, it's always going to be cheaper to do that, right? Because the biggest part here is this global model. The attention mechanism inside this global model is the most kind of intense part of it. So you take your sequence, you cut it up into chunks, and then the global model only looks at the sequence of those chunks. But I mean, there's something a little bit, they're doing a little bit of kind of like hand waving here, because that's literally what this is what a tokenizer is doing as well, right? When you take a sentence and you tokenize it into these, right, the total amount of individual letters in your sequence is going to be bigger than the total amount of tokens in your sequence. So tokenization is already doing that, right? In effectively, everything that they described here also applies to tokenized transformers, right? There is some sequence length t, which is the actual size of your sentence. The patch size p, you could just replace this with the average number of letters per token. And then you would basically get this. However, attention is not the main cost in large transformers. Instead of increasing the sequence length, transformers are more commonly scaled by increasing the dimension of their latent space d. And the feed-forward network cost dominates the model's overall cost. For example, in GPT-3 architecture, the quadratic self-attention computation accounts for 1.4% of the flops. Huh. That's actually kind of interesting. I didn't realize that. So the self-attention isn't actually expensive in terms of operations, right? This is flops is floating point operations per second. So that's like actual, it's like multiplying matrices together, like those, like actual operations that your computer's doing. So the quadratic self-attention, really, it's only bad because of the memory footprint, but it's not actually that bad in terms of the total operations, which is interesting. Floating points flops per token for different model architectures at different scales. Megabyte architecture here using p equals 8. Use less flops than equivalently sized transformers and linear transformers across a wide range of model sizes and sequence lengths. So here you have different transformers of different sizes. So you have a 604 million parameter transformer, you have a megabyte of similar-ish size, 616 million parameters. And you can see here as the size of the sequence increases, the total amount of flops required kind of stays flat and then slowly increases. So blue is the megabyte. So you can see that blue here has the lowest amount of flops per token compared to these other ones here. Following the approximation, a forward pass with a large transformer with m non-embedding parameters on a sequence length t roughly uses 2mt flops. Megabyte contains two transformers. The global model uses mg parameters on a sequence of length p t over p, and the local model with ml parameters that sees t over p sequences of length p. Right? Giving an estimate of 2t mgp plus ml. So they're basically just taking the fact that they have two different transformers here. One of the transformers is acting on this sequence here, which is basically the size of your original sequence but cut into these patches, so divided by 4 in this case. And then you have a different transformer here, but there's going to be basically a bunch of these in parallel, so you're going to have to do each of these. And these have a smaller little sequence. So when you plug that into this approximation here, which I guess comes from this paper, there's some paper over here where they came up with this rough rule of calculating the flops required for a transformer. They plug in these numbers in here. You end up getting this. When mg is much greater than ml, the flops used is approximately 2t mgp. So when mg is much greater than ml, you can basically cancel out this ml here, and you end up getting 2t mg over p, which is what they're showing you here, allowing a model p times larger than a transformer with equivalent flops. Okay, so they're basically saying with normal transformers, you're limited by this, by 2mt flops, but because whenever you plug in this megabyte, you get 2mt, in this case the m is mg, the size of the global one, over p, it means you should technically be able to get away with a transformer that's p times bigger than that, right? Because you would be able to say mg times p, and then it would cancel out, and you would get m2tm. This analysis holds irrespective of any efficient attention mechanism used in the transformer. Yeah, so this makes sense, but I think that the problem here is that the the amount of memory used is still kind of an issue, right? This is just talking about flops, but I think the total memory is almost a bigger problem. To understand efficiency at different sequence lengths and model sizes, we calculate the total flops used by transformers, linear transformers, and megabyte. We use flop estimates except for attention in linear transformers, which we estimate as 9D flops per token, where D is the model embedding dimension. Figure 3 shows that for models of size 660 million, 273 billion, and sequence lengths up to 1 million tokens, MegaByte with p equals 8 uses less flops than either transformers or linear transformers. Baseline model architectures are based on GPT-3, and MegaByte local global model sizes are 452 and 151. So actually, this is giving you a size for the two different parts here. So the global transformer is roughly 4 times the size of the local one. So this global one here is roughly 4 times the size of this local one, which is interesting because the patch size is also 4. So there's like kind of these weird relationships between the relative sizes of these things. I guess maybe not here. The p equals 8. Never mind. Generation efficiency. Generating long sequences with transformers is slow because the input to each time step is the output from the previous time step, meaning each layer must be computed for each token serially. Yeah, this is kind of what I was describing before, where the way these transformers work, you basically have to feed, in order to get this word, you need the previous word, and then in order to get this word, you need the previous word, in order to get this word, you need the previous word, so they have to basically do it one token at a time. Like all transformers are operating one token at a time, which is very slow. But in this one here, MegaByte, you can do it in parallel, right? You do the entire. It's still not fully parallel because it's like you're not going to have, when you're decoding, you're still not going to be able to know what the future one is, but running a layer on a single token typically does not saturate the amount of parallelism available within a GPU. For analysis, we model each layer as a constant cost independent of size. Consider a MegaByte model with L global layers in the global model and L local layers in the local model and a patch size P, compared with a transformer architecture with L local plus L global layers. Generating each patch with MegaByte requires a sequence of O L global plus P times L local serial operations. Again, big O notation for the total amount of operations required. Whereas the transformer requires O of P times L global and P times L local, right? Because it's not cutting it into P patches. When L global is greater than L local, i.e. the global model has many more layers than the local model, MegaByte can reduce the inference cost by a factor close to P. Yeah, I mean, they're really stressing this point, but you're not doing a fair comparison, right? Because at the transformers are already cutting down the sequence, right? Like Bard isn't looking at this byte by byte. It's looking at it in tokens, and the tokens are probably little chunks of words like original, word, piece. So it's already cutting up the input sequence into tokens, which are, there's less tokens than there is individual characters in the sequence. So this is already happening when you're using a transformer normally. You're already cutting it up into a smaller sequence. So this is it's a little bit misleading because it's like they're almost like pretending that transformers are also looking at things byte by byte, but they're not. They're looking at it token by token. Controlling for compute and data. Models show consistent improvements when increasing both data and compute, meaning that one model can outperform another because of increased training budget instead of an improved architecture. Okay, I mean, this is Deep Learning 101. You make the data bigger, you make your compute budget bigger, you train it for longer, you have a bigger model. Anytime you use the word big, it gets better. However, in practice, both compute and data are typically limited. That is true, right? It's like you have some limited amount of money that you can spend on AWS. You have some limited amount of GPUs that you can train on at home. You have a limited data set that you can collect. So it seems like the model could be generalized to more than 2 levels of hierarchy of transformers, to n levels, where the innermost transformers look at higher level tokens. Yeah, you can take any hierarchical approach and just keep adding more hierarchical layers to it, right? You could envision a version of this where you have a million bytes and you break it down into 500,000 bytes, and then you have two global models, which each of them feeds it into an even bigger global model, right? So yeah, you could choose to break up this entire pattern here into even higher levels of hierarchy, right? So here they're going from individual bytes into patches of size 4, then feeding all of those into a global model, and then going back up here. But you could see it breaking up into patches of size 4, potentially even having more patch embeddings, more global models that continue to just break down the sequence into smaller and smaller things. So yeah, any hierarchical approach, you can always just add more layers, right? We conduct experiments using a fixed compute and data budget across all models to focus comparisons solely on the model architecture. I think this is good. I don't want them to necessarily use a bunch of uh, tricks in order to get a state of the art. What I want to do is I want a fair comparison between this architecture and the vanilla transformer architecture. We train all models for the same number of bytes. We compare MegaByte with both a standard decoder-only transformer and perceiver AR. Okay, perceiver AR is a variant of the original transformer with a single cross-attention layer over a much longer context sequence, and is the best performing general-purpose autoregressive model we are aware of, and achieves state-of-the-art results across several modalities. Oh shit, maybe we have to look at this perceiver AR paper. What is this? Perceiver AR. Perceiver AR is a paper out of DeepMind that apparently gets state-of-the-art on a bunch of things. There's a lot of names. We've developed Perceiver AR, an autoregressive modality agnostic architecture. So again, you see this same kind of theme where they want to basically not rely on a tokenizer that is specific to text. They want to be able to do something that's more generic. Can directly attend to over 100,000 tokens. So what exactly is it doing here? Perceiver AR. You see here how each letter here is turned into a token. That's not exactly how the tokenization would work. It would actually be like for a little group of letters, but just for this figure, they show it to you this way. And then each of those tokens, here you have the cross attention, and the cross attention is only done. Oh, this is kind of tricky. You see how they're doing, they have the sequence here, and then they only do the cross attention for everything after. So this attention matrix here is smaller because of that. And then they're somehow getting these latent vectors, and then you see here how they're doing cross attention in the latent vector space, which means they can abuse the fact that this is going to be a smaller. So it's kind of like the same way how you do diffusion in the latent space in order to save compute. Maybe here what Perceiver AR is doing is it's doing self-attention in the latent space to save on compute. But I don't know. I haven't read this paper, so don't necessarily take that. That's just me looking at this paper for 2 seconds and trying to determine what they do. But maybe one of you guys actually read that paper and you can let us know what they're actually doing. Either way, they're comparing to this Perceiver AR, which is basically the current state of the art. We implement both models in the same code base, and all models share similar data, loader, preprocessing step, and trainer in order to avoid any artifacts. So I wonder what preprocessing they're doing in terms of text data. Generally, preprocessing is in computer vision, what that might mean is opening the image, normalizing the image, adding augmentation, making sure it's the right size, and then feeding it to your model. Pre-processing in terms of text might be just tokenization, taking your text, breaking it up into tokens, and then using those vectors. But I wonder if they count the tokenization as pre-processing because their model doesn't require tokenization. All models were trained using the MetaSeq code base, and the training used PyTorch. Of course, in a meta paper, they're going to be using PyTorch, which makes a bunch of sense, with fair scale to improve memory efficiency through fully sharded model and optimizer states. So what do they mean here by sharded model and optimizer states? So when you train something locally on your computer, the entire model is inside your one GPU, and the optimizer states, aka all the little variables inside the atom momentum, for example, or all the different partial derivatives, those are all basically stored on your computer. But when you have a more complicated distributed training setup, one thing that people do is called model parallelism, where they take the model and they shard it, right? A shard is an English word for like a piece of a stone, right? So a sharded model and optimizer state means that they're taking these numbers, which represent the model, and then the numbers that represent the optimizer states, and they're sharding them across a variety of computers. And there's like a billion different ways of doing that are all depending on whatever hardware you're using, so I'll stop there. Mixed precision training refers to training where you're basically not using necessarily float 32s all the time. Sometimes you're also using float 16s. You're using lower precision data types for specific numbers that you know you don't necessarily care as much about, and that allows you to basically do things faster and use less memory. More training details in various models can be found in section 8.1. To validate our implementation of Perceiver AR, we produced their experiments on downsized ImageNet at 64 pixels. Okay, so ImageNet is already kind of a small. ImageNet is an image data set, but the images are actually pretty small, right? So downsized ImageNet is even smaller. So like you get to a certain point where it's like, what the fuck are you even doing, right? Like what are you looking at when you're looking at downsized ImageNet? like ImageNet is already very small. I feel like if you downsize it, it's even like can you even like do anything with that? We achieve a bits per byte score of 3.53. So kind of what they're talking about here is that this Perceiver AR is a DeepMind paper, so they did not release this, right? They released the paper, but they did not release the code. So they want to be able to compare against this Perceiver AR, but they don't have the code, and the people who work at DeepMind aren't going to give the code to these random people at Facebook. So they had to re-implement Perceiver AR, right? R implementation. They re-implemented Perceiver AR, but the problem whenever you re-implement something based on a paper is that there's a lot of stuff that they don't tell you in the paper, right? Like hyperparameters, right? What is the momentum for this optimizer? What was your learning rate schedule? What was the exact type of mixed precision training that you used, right? There's all these different hyperparameters that they don't necessarily tell you. Here they said they match them, so maybe in this Perceiver AR paper, maybe they do tell you the hyperparameters. Let's see. Generally, they tell you in the appendices. Yeah, I mean, they're telling you some of them here, like number of steps, warm-up, constant learning rate, cosine decay, which is a type of learning rate scheduling. They're telling you the exact dimensionality of all the different layers and heads. So maybe they were able to basically produce a pretty good copy, but what they're saying is that, okay, we tried our best to re-implement Perceiver AR We tried to match all the hyperparameters, and we got a score of 3.53, which is what they compare, which in the paper they got 3.54. So those two numbers are close enough that we're just going to guess that our implementation of Perceiver AR is just as good as the Perceiver AR that's sitting on some server in Google DeepMind's office. The server is actually probably not in the Google DeepMind office, but that's what they're letting you know. Several techniques have been proposed for trading off speed for performance during inference with language models, including sliding windows and our strided inference. Sliding window and strided inference are the two techniques that they described earlier in terms of trying to improve the fact that they're not translation invariant in their technique. We evaluated the performance of MegaByte on language modeling on a set of 5 diverse datasets, emphasizing long-range dependencies. So these are some datasets here. Project Gutenberg, books, archive, and code. The PG19 dataset consists of books written before 1919 and is extracted from the Project Gutenberg online library. Okay, so you have a bunch of basically English. I guess they also have code. That's kind of cool. They have code. They have archive papers. Look how nice that little LaTeX is. Archive. Table 7 lists BPB. BPB is this right here. It's bits per byte, which is some kind of score. For each dataset, each model is trained for 80 billion bytes, and models are scaled to use the same compute budget. We carefully tune hyperparameters for all architectures to best utilize the compute budget. MegaByte consistently outperforms both baseline transformers and Perceiver AR across all datasets. We use the same sets of parameters on all datasets. In all experiments, transformer has size 320 million with context length of 1024. Perceiver AR has 248 million with a context size of 8,192. And MegaByte has a significantly bigger size. Okay, that makes sense. So this entire time, in this paper, they're saying, okay, well, if you keep the compute budget the same, because our thing is cheaper in terms of compute budget, that means that you could have a bigger model. So it's they're saying, okay, we're comparing a smaller Perceiver AR with our bigger MegaByte because both of them have the same compute budget. But is that necessarily the right comparison, right? Wouldn't you prefer to see a MegaByte that is smaller, that is the same size as Perceiver AR, and then just say, hey, it's the same size, it performs a little bit worse, but it's faster? But they'd rather say, hey, it's the same speed, but it's bigger, and thus it performs better. Performance of compute and data controlled models on various text modalities. Here are all your different data sets. I guess lower is better for this particular bits per bytes metric, and they show you that they're better. This one seems significantly better. You got 81 and 79, and then it goes down to 67. You got 57, 54. This goes down to 41. This is the relative size of the different data sets. So archive, I guess, is 90 gigabytes. Code is around 400 gigabytes. We scale up our training data on PG19 and compare MegaByte with byte baseline, as well as converting all results to word level perplexities to benchmark with state-of-the-art token-based models. So, token-based models, the perplexity is going to be at the token level. So in order to compare, they need to basically convert their bytes into words. How performs other byte level models? We also compare with the best previously reported numbers for subword models. These results may be confounded by differing amounts of compute and tuning, but show that MegaByte gives results competitive with state-of-the-art models trained on subwords. These results suggest that MegaByte may allow future large language models to be tokenization free. Yeah, I think this is really the biggest part. Image modeling. We test MegaBytes on variants of autoregressive image generation task on ImageNet to measure its ability to efficiently use long context. Autoregressive image generation, I think that's just basically taking the image and generating it basically almost pixel by pixel. They do it on different size images, so 64 by 64 to 640 by 640. Right, and 640 by 640, if you're predicting each pixel almost as if it was the next token, effectively what you're doing is you're predicting over 1.2 million tokens. This generation task becomes increasingly challenging as the image's resolution grows, because you need to basically generate individual pixels that not only do well in terms of the local pattern, right, textures, lines, things like that, but also needs to be capturing the semantic high-level information, such as the fact that this is an image of a dog or something like that. The model image data patch by patch. Okay, so they're not actually doing it pixel by pixel, they're doing it patch by patch, where the patch is probably, I don't know what the patch is going to be, maybe 8 by 8, 16 by 16, something like that. Comparisons with state-of-the-art. We train a large MegaByte model on ImageNet 64 with global and local models sized around 2.7 billion and 350 million parameters for 1.4 trillion tokens. We estimate that training this model consumed less than half the GPU hours we would have needed to reproduce the best perceiver AR model. It's kind of interesting. So maybe not only is it computationally faster and more efficient, which means you can have a bigger model, but maybe it actually learns faster. Scaling to higher resolutions. We compare 3 transformer variants to test scalability to longer sequences on increasingly large image resolutions. We use our own implementation of these in the same framework and budget the same amount of GPU hours and data to train each of these model variants. Damn, they like implemented every single... They implemented their own transformer, their own perceiver, and of course they implemented MegaByte because that's the paper. MegaByte is able to handle all sequence lengths with a single forward pass of up to 1.2 million tokens. We found neither the standard transformer nor perceiver AR could model such long sequences at a reasonable model size, so instead we split the images into segments of size 1024 and 1200 respectively. So 1024 square root of that is 32. So they're cutting the image into patches of size 32. For MegaByte, we set the patch size as 12 and then 192. So I guess not. That doesn't make any sense. 12 squared? Is 12 squared 224? No, it's 144. What the fuck are they talking about? Math doesn't work out here for the patch size and the segment size. Model sizes are adjusted. Oh, no. Okay, their patch here, they're referring to the size of the patch for the MegaByte, not the size of the segment, not the size of the patch that they're breaking the image into. Okay, that makes more sense. Model sizes are adjusted to match overall training speed across models, and we do not use any form of sliding window in this experiment. MegaByte outperforms the other systems at all resolutions, demonstrating an effective model of sequences over 1 million bytes. We evaluated the performance of MegaByte on language modeling on a set of 5 diverse datasets. The sentence piece tokenizer. Let's ask Bard. How does word piece tokenizer compare to sentence piece tokenizer? are both subword tokenizers, which means they break down the words into smaller units called subwords. Are both based on the same principle. Word piece, greedy algorithm to merge characters, uses a unigram language model, creates a vocabulary of subwords, creates a vocabulary of unique tokens. Easier to use, produces shorter tokens, is more complex to use, produces longer tokens. Okay. So this is the tokenizer that they're using for their baselines against these other types of transformers here. Of course, these tokenizers have a limited vocabulary size of 32,000 possible tokens. This paper, the MegaByte, does not tokenize, but it converts individual bytes into one of 256 possible values, which is, there you go, that's technically the vocab size. I like this because this basically shows you very clearly that, you know, the one thing that I keep saying in this paper that kind of annoys me is that they're kind of pretending that they got rid of the tokenizer, but they didn't. They just are using bytes as the tokenizer. That's kind of, so I like that in this table they kind of make it very clear that, hey, there is a vocab size. We are basically tokenizing. It's just that we're tokenizing with something that's much more simple than a pre-trained tokenizer like a sentence piece. Have to head off now. Thanks for dropping by. Thanks for the comments. They're really helpful. Context length 512 plus 1024, 512 plus 512 plus 2 times 512. Validation test. Validation test. So I guess here lower is better, and then here, ooh, this block recurrent over here. Look at this score. This score is really good. 26. Holy shit. Larger scale experiments converting bits per byte to word level perplexities for comparison with prior work. So they're taking this metric here, bits per byte, and changing it to word level perplexity, which is also a different metric that you can use. But the reason they want to use word level complexity is that some of these benchmarks here only have numbers for this word level perplexity. So they're changing the bits per byte, which is the metric they were using for this evaluation here, into perplexity. MegaByte outperforms other models by a wide margin. I don't know if competitive is the right yeah, this is a little bit misleading too. So basically they're saying perceiver AR byte, which is they naively take the perceiver AR and then feed it basically these byte tokens, and it performs terribly. But if you take perceiver AR and you use the original tokens that it was intended to use, right, these sentence piece tokens, it performs much better, 28. So you're outperforming transformer models by using those transformer models in a way that they were not intended to use. And the MegaByte model, in the way it was intended to be used, is not really that competitive with these other models here, right? We're talking 26, 28. Those are significantly smaller numbers than 36. I don't know. I'm also not necessarily a natural language processing NLP person, so I don't know whether a perplexity score of 36 versus 26 is a big difference. Maybe if one of you is more in this field, you might have a better intuition around perplexity scores, but just looking at this, I don't know if that's necessarily competitive. The ImageNet task, so this is basically where they take ImageNet, downsize it, and then try to almost pretend like every single little pixel is like a word and you're trying to predict the next word. MegaByte does quite well, but it's about the same as these other ones. This is weird. Table 6 is literally a copy of this other table here. Table 1 and Table 6 are the same. What the fuck? Duplicate tables. Bits per byte. And different sizes of the ImageNet task. So you can see that ImageNet 640, which is basically a bigger size image, which means that the sequence length is longer. MegaByte ends up doing pretty well. Controlled experiments. List BPB on each dataset. The model is trained for 80 billion bytes. We carefully tune hyperparameters to best utilize the available compute budget. We scale up our training data on PG19 and compare with MegaByte with byte baselines. We train a byte level transformer, perceiver AR, and MegaByte models. I don't know if that's a good thing. I don't feel like a byte level perceiver AR means anything. The perceiver AR paper was not designed to work with bytes like that, so yeah, outperforming a model used in not the way it was intended is not necessarily impressive. May allow future large language models to be tokenization free. I agree with that. Auto modeling task. Audio has both aspects of both the sequential structure of text and the continuous nature of images. Raw audio is typically stored as a sequence of 16-bit integer values, one per time step. A softmax layer would need to output 65,000 probabilities per time step to model all possible values. So raw audio is a waveform, right? So it's basically this one-dimensional line that goes up and down. And if you store it in a 16-bit integer, you have a total amount of vocabulary size of 65,000. So various techniques have been developed to reduce the memory and computational requirements of the softmax. Van der Oort, I think this is the WaveNet paper. Yeah, this is WaveNet. So this paper is very good. If you guys are into deep learning papers that are a little bit older, this WaveNet paper was really cool when it came out. So there's some trick there where they apply a mu-law command transformation and quantize the input into 256 possible values, which is very convenient for these guys because that's the exact vocabulary size that they've been using. Use a dual softmax technique to produce 8 coarse and 8 fine bits. So kind of other techniques that people have come up with to reduce the vocabulary size of audio data or an audio sequence. 16 kilohertz, 16-bit audio. We use an extensive audio dataset consisting of 2 terabytes of audio. What is this dataset? That's very sketchy. Facebook has a 2 terabyte audio dataset that they don't want to talk about. Is that the dataset that they collected by secretly listening to your cell phone every time you scroll on Instagram? Why don't they tell you what that is? That's a little sketch. We use a sequence length of 524,000, patch size of 32, batch size of 32 to facilitate model training. Our model obtains a BPB of 3.4, which is much lower. I don't have a good intuition for BPB, to be honest, so I don't know how much better 3.47 is compared to 3.54, but I guess it's lower. We also compare the text generation speed between MegaByte and a transformer. We compare a 350 million parameter baseline transformer and MegaByte model with a 1.3 billion parameter global model and a 218 million parameter local model. MegaByte model achieves much lower perplexity, also generates a sequence of 800,000 tokens 40% faster than a transformer, despite having over 4 times the parameters. That's impressive. The speedup is due to the bulk of the parameters being in the global model, which only needs to be computed once for every 8 tokens, whereas all the parameters in the baseline model are used on every token. Yeah, so I feel like I've explained this 4 times already in this paper, so I apologize, but this global model only needs to be run once for the entire sequence, versus in most transformers, you're running it every single time you perform inference for every token. Model components. We analyze the significance. Oh, wait up. We forgot about these tables here. What do we got? Figure 4. Average log probability assigned to the token at different positions within the context length by MegaByte model with a 8,000 context size and by a vanilla transformer model pre-trained using the same amount of compute. MegaByte likelihoods rise throughout its context window, demonstrating that it can use tokens from 8K bytes previously to improve its predictions. So average log probability, token position within the context window. MegaByte has a higher average log probability even as the token position within the context window increases versus a vanilla transformer, because it only has a limited context length. Once the token goes past the context window, the average log probability kind of stops, I guess, and becomes flat. Assigned to the token. We don't know what this token is. Maybe it's the correct token. Average log probability assigned to the correct token based on whatever data set and ground truth we have. Right, so I don't know. I don't really know exactly what I'm looking at here. I guess it's better. I'm tired. Don't judge. In Table 10, we analyze the significance of different components in the MegaByte architecture by studying these different data sets here. You got Archive, LilyBright, and ImageNet 256. Removing the local or global model, we observe substantial increase, showing that both parts are crucial. Okay, so they're doing an ablation here. They're getting rid of either the global or the local model, and it doesn't perform well if you remove either of those. You need coffee. I do. Let me drink more of your pomate. The performance of the model without the cross-patch local model is competitive, indicating that the architecture is robust to this modification. We observe slight improvement on the LilyBright L and ImageNet 256 by augmenting the MegaByte model with a CNN encoder. Okay. So this is interesting, where in the ImageNet task, rather than feeding in the pixel values directly, they're going to take the pixel values, encode them with the convnet, and then feed in those the encoded values, which is, I think, what a lot of vision transformers do as well. Not in this one. This one has flattened patches, so they're taking these patches and just flattening them out. But sometimes you'll see vision transformers where they take this patch and then they encode it, and then that's what they feed into the transformer. Yeah, so this is what a encoder looks like. So actually, here you go. This is literally exactly what I was saying, that sometimes you take the image, encode it into basically these feature maps, or you can think of these as kind of like tokens, right? They're basically just embeddings, and you feed that into the transformer. Effective use of context. Long context models often struggle to benefit from the full context. Figure 4 shows that later tokens within each context window consistently have a higher likelihood. Oh, okay. I think I know what they mean by this. Okay. So I think what they're showing you here is that as you have more and more uh, stuff in your context, the model becomes more and more confident about the next word, right? So let's say you're here, right? And I give this prompt, and then Bard adds this token to it, and then it adds this token to it, and then it adds this token to it. The first couple tokens that it adds, right, the tokens at the beginning, it's less confident about them, right, because there's just less context. It doesn't really know where the answer is going and what the correct answer is. But like the more you go along the thing, the more further you go, the more confident the model becomes, because it's like, oh, okay, I know what I'm doing here. I know what this answer is going to be like because I already have a bunch of kind of context. It's like the more of the answer I have written down, the more confident I become in the next token, which is what you're seeing here, right? You're seeing that initially the first however many tokens, it doesn't really have a high confidence about what the next token is, but then increasingly as it keeps giving you more and more and more, it becomes more and more confident about what the next token is. And it says that MegaByte, this trend continues even if you keep going into 8,000 tokens, versus this vanilla transformer, at some point it stops because it just doesn't even have the context length to analyze anything beyond that. Okay, that kind of makes sense. We find that within a single patch, on average, the MegaByte performs worse on later tokens within a patch. Okay, so this is the strided inference crap that they were talking about, where they're going to be doing 2 forward passes and then they're going to offset their sequence by p over 2 tokens. Tokenizer, context, vocab. This is the same exact, we literally just saw this. They have some duplicate figures in this paper. It's kind of weird. Generation speed. So they're comparing to an 8,000 byte transformer model, 8,000 context, 8,000 byte context, which is normally a 1,000 token context. And it's much faster. Ablation of MegaByte model components, showing that both local and global models are critical to strong performance, but the architecture is robust to other modifications. So here is all the different ablations. So if they get rid of the local model, it does pretty bad. If they get rid of the global model, it actually doesn't do that bad. That's just kind of surprising. Look at that. 3.18 versus 3.15. The global model doesn't actually even do that much. Actually, it's even weirder. The global model is not important for the ImageNet task or the audio task. You see that? It's not that important for the audio or the ImageNet task, but it is very important for the archive task. Which makes sense, right? In a modality like text, being able to look at the whole text and the global text, right? The global information in the archive paper is very important because you need to be able to predict individual token, like the local stuff depends on the global stuff. Versus in ImageNet image or in an audio, it's more dominated by kind of the finer details, so I guess the global model doesn't actually do that much. You don't need to know the entire content of the image to just generate little patches of the image. This is kind of a cool little result right there. Cross-patch attention and CNN encoder. Kind of cool that the CNN encoder improves the audio generation. MegaByte introduces several additional hyperparameters. We tuned these hyperparameters independently for different modalities and reported performance on the best settings we found. Ooh, that's a little sketch. You don't want to have hyperparameters that you need to be tuning for each individual modality, but got to do what you got to do, right? We experimented with various patch sizes on image 256 dataset and found that there is a wide range of values where MegaByte performs similarly. We found similar robustness against the choice of this hyperparameter across all modalities, although the optimal patch size itself can be different across modalities. Original inference, shifted inference, used tokens, discarded tokens, log probability, position, and sequence. So this thing here, right, they're talking about the strided inference. So really what they're saying is that the inference is being done like this, where they're breaking it up into this kind of blue bar here, these 4 patches here, and then they do the same thing, but they break it up into patches that are shifted. So then they run inference on both of those, and you get, by doing it with the blue and then doing it again with the green, or whatever this color is, this like weird yellow, and then you discard these tokens. So the problem with this is that you have to do inference twice. You have to do inference with all the blue things, and then you have to do inference with all the yellow things, and then you basically end up throwing away half your answer. Yeah, so strided inference is going to double your inference cost. Sliding window also going to double your inference cost, and if you do both of them together, it's going to 4x your inference cost, and that gives you the best score. But if you 4x your inference cost, isn't that literally the yeah, this is a little sketch. So right, they keep talking about how their model is very fast and very efficient, and it's better than transformers, but if you use it in the way that actually leads to the best performance, you actually have to compare against 4 times that. So is your model with 4 times the amount of inference cost also competitive with the original transformer? I don't know, right? Now it's starting to get a little bit more murky because they're comparing the simplest version of their model with the best, like kind of not a good, right? This perceiver AR on bytes. There's like some shenanigans going on here, the way that they're comparing things. Local to global model size ratio. We experimented with different local global model sizes by grouping bytes into patches. MegaByte. They compare the 2 results, or what do they do with the outputs? Yeah, I'm more saying that like here, right? They're comparing perceiver AR to MegaByte, right? But this MegaByte doesn't account for this, so this is like MegaByte like this. So really, in practice, would you end up using this in order to get the slightly better BPB? And in that case, then this MegaByte here would actually take much longer than any of these other ones. That's kind of what I'm saying, is that they're kind of picking and choosing the right things to compare about. How do they choose the correct token if the offset inference gives a different result? So it looks like they just discard them, right? So it looks like basically they offset the inference. So they have the offset is the blue, and then they have the blue is the original sequence, and then they feed in also the offset sequence with this yellow, and then I kind of agree with you that I feel like they should have combined these. They should have taken the output of the blue here and somehow combined it with the output of this yellow. Maybe added those log probabilities together, but instead it seems like they just throw away the second half of the blue because it tends to have a higher log probability on the beginning. Yeah, so they're just throwing away the offset whenever they overlap. They're throwing away the overlap of the offset. We find that a given compute budget is spent optimally when the global model has more parameters than the local model. This trend was consistent across all modalities. Okay, so they try a couple different sizes of the global size and the local size. So the local is the size of this thing here. The global model is this thing here. So they're trying different sizes for the global model, different sizes for the local model. So different dimensions too. These numbers are all pretty close. So they aren't comparing the two sequences, just discarding the work they do. That's what it seems like. It seems like they're just discarding, at least in the strided inference, right? So whenever you're doing it normally, you're like if they were just only using the 1 times 1x basic inference, they would be basically saying they would choose these bytes here, right? All of these bytes. They would use the byte here, then the byte here, then the byte here, then the byte here. But when they're doing this shift strided inference, then they get 2 of them, right? Because they do inference twice, they have, for some of them, they have 2 tokens, 2 possible tokens. They could either use the one that this inference told them to use or the one that this inference told them to use. And it sounds like they're just basically discarding them. I would have added them, right? I feel like you could have added those together and then maybe you get a better token, right? If the first inference is telling you this is probably the byte that you want, and then the second inference is telling you this is probably the byte that you want, right? Both of those things are giving you a probability over a 256 dimensional vocabulary, right? So why not just add both of those together and then take the softmax of that? Several related techniques to ours have been developed. In particular, patchifying operations have been previously being used in image encoders, and down and up samplings have been used for text encoders. But such methods cannot be naively applied to decoder-only models without leaking information to future bytes in the same patch. MegaByte generalizes these approaches to an efficient decoder model by using an intra-patch transformer to predict each sequence element's likelihood, and offsetting the inputs to the 2 models to avoid leaking information. Use self-attention on a shortened latent sequence also resembles patchification, but this technique cannot be easily applied to decoder architectures without leaking information to future time steps. This leaking information that they keep talking about is whether or not there's a path that information can use to go from the future into the past, basically. So you see here that this one can only pay attention to 1. If there was like a line here that could connect this, then you could kind of cheat that way. Improving the efficiency of decoder models is more challenging because of the need to make 1 prediction per time step and not leak information for future time steps. The most popular approaches can be categorized as chunking sequence into smaller blocks, cross-attention, linear alternatives, which typically involve forms of token-level recurrence, state space models, sparse approximations of attention. However, the performance of dense attention means that it's typically still chosen for large-scale decoders. Yeah, I also think just dense attention is easier to conceptualize and easier to implement. That's why these kind of like weird, like 500 IQ sparse types of attention haven't like necessarily caught on. MegaByte takes the alternative approach of decomposing the complete sequence into 2 shorter sequences, giving subquadratic attention. We also note that feed-forward networks are the dominant cost in large decoders, not self-attention. Yeah, this was kind of interesting. I did not know that it was that crazy. It's like literally 1.3% they said. I would have assumed it was higher than that. Yeah, where was it? I think it was up here. Where is it? Where do they tell you that? I remember reading it. Yeah, right here. Quadratic self-attention computation accounts for only 1.4% of flops. Like, that's fucking crazy. I would have, like, if someone had a gun to my head before I read this paper, I would have guessed way more than that. Our approach to compressing sequences also allows much larger models that would be possible when using large feed-forward networks at every time step. The most common approach to shortening sequence lengths in transformer decoders is to pre-process the input with a form of tokenization. Yep. Tokenization is not just about converting words into vectors that are easier to deal with. It's also about shortening the total amount of length in the sequence. Multiple bytes are mapped into a single discrete token. For this text, this can only be done losslessly using methods such as BPE and sentence piece. But these approaches can require language-specific heuristics and limit out-of-domain performance. Yeah, the tokenizers are going to be specific to some language that they were trained on or some distribution that they were trained on. So, in a sense, you're kind of limiting your final performance by using a tokenizer. The amount of high-frequency information for images and audios means that tokenization cannot be performed losslessly, and instead clustering or discrete autoencoders are used to compress the inputs. You can have lossless tokenization. How is tokenization lossless in text? I mean, this is what I've been explaining to you guys, is that to me, tokenization, you're inherently losing information because you're basically compressing it down, but it sounds like you can basically, in language, you can have lossless tokenization. The original meaning of the text is preserved even though it may be represented in a different way. Yeah, okay, I mean, this is contradictory here. The original meaning is preserved, but uh, it can make it more difficult to track the meaning. So which one is it? My intuition is that when you tokenize anything, including text, you're fundamentally altering the distribution of the input. You're taking an input distribution, which is normally words in a sentence, like letters and words in a sentence, and turning it into this sequence of tokens. And that is fundamentally different, and therefore you're kind of like corrupting the data. So, do you think tokenization is here to stay? I don't know. Probably, maybe. Tokenization will still exist because even what they're doing in this paper, right, where they're converting individual letters into bytes and turning it into this 256 vocabulary token, that's still tokenization, right? If you inside transformers, Hugging Face transformers, there's probably now a byte level tokenizer. Hugging Face transformers byte tokenizer. So here's a byte pair encoding tokenizer. I don't know. I just feel like they're just gonna put this exact thing here, this 256 byte, and they're going to make it available inside this tokenization library because you use it largely in the same exact way, right? You're basically just taking uh, a sentence and then turning it into a sequence of tokens, except here the tokens are per letter and they're much smaller, the dimensionality of that token, but it's still the same thing. The patches, yeah, our patches are analogous to traditional lossless tokens, and the local model performs the role of mapping a hidden state to a distribution of where possible patches. Conclusion. We introduced MegaByte, a scalable architecture for modeling long sequences. MegaByte outperforms existing byte-level models across a range of tasks and modalities, allowing large models with sequences of over 1 million tokens. It also gives competitive language modeling results with subword tokens or subword models, which may allow byte-level models to replace tokenization. Yeah, I just feel like bytes and tokens are the same thing. It's just two different words describing fundamentally the same thing. However, the scale of experiments here is far below those of state-of-the-art language models, and future work should explore scaling MegaByte to much larger models and datasets. You can bet that they're probably doing that. That's that. Let's see. Anything interesting in the appendices? Of course, they're using Atom Optimizer. Polynomial decay learning rate schedule. Fancy learning rate scheduling. Little ReLU activations. Little dropout. Little weight decay. Local size, global size. Batch size and learning rate. Look at this batch size, 1,536. That's a huge batch. Little misspelling there. Number of layers. Pseudocode for MegaByte model. Class MegaByte decoder. You have one global model, one local model. Both of them are instances of the same transformer decoder class. The forward pass prepares the input. This is where you would have your tokenizer, right? You would just have an extra thing here that says convert. You would basically here you would have text and then something that goes from text to bytes in the same way that in a subword or tokenizer type transformer you would have words and then you would go from text to tokens. Global model embed, the global rearrange. So this is the reshape. No, this is not the reshape. This is the reshape. You take the output, reshape it. This is the previous token plus the output. Oh, shit. I was going to show you that on the picture, but... And this is the prepare. Pseudocode is literally Python. Yeah, Python is pseudocode, basically. Python is like the highest level programming language. That's why it's so popular. But I think actually, if I had to predict, I feel like Python is going to disappear. And 10 years from now, there will be something that, like what Python did to C, something is going to do to Python, right? Like think about that. Python is actually C, like underneath all of it, underneath Python is really just basically C code. But a lot more people use Python than use C because it's a lot easier to write in Python than it is to write in C. You can basically, it almost reads like English, you know? but it's not exactly English. And I think that's the main thing, is that at some point someone's going to make a programming language that is basically just English. It's just like text. You just write it like a paragraph, and that will compile down into Python, which will compile down into C, which will compile down into machine code, right? So if I had to make a guess, I feel like someone is going to make a programming language that is basically whatever Python is to C, this new language will be to Python. Do you think the report that OpenAI is going to release an open source LLM is true? Probably. They're probably just going to open source GPT 3.5. I think Sam Altman read that paper about Google that we don't have a moat and neither does OpenAI, and then he's probably convinced about open source potentially disrupting OpenAI. So he's going to try to push for open source, and then at the same time, of course, he's going to go to Congress and ask them to make it illegal for anybody but Google and OpenAI to push models. So they're going to try all the things. They're going to try to be part of open source while they simultaneously try to regulate it so that open source doesn't exist anymore. Just think about how weird that is. Like, imagine you're sitting there in your house training a language model. You're tuning a LoRa for Llama 65B, and then the police break down your door and they come in with guns and they're like, you need to kill those GPUs. You're not allowed to be training that model. That's illegal. Like, what? It's such a weird future where it's like illegal to train language models. We train the model by sampling random spans. What do we got here? This is the image. So when they're doing the ImageNet, they're basically treating ImageNet as if it was like a sequence. Patch scan versus raster scan. So raster refers to this approach where you're going just all the way around, but patch scan is what they're doing in the vision transformers here. Not this one. This one. So they first break it up into these patches and then they flatten the entire patch. So that's what this is. Cool. That's it, guys. That's it. That's all 16 pages of MegaByte. You've officially made it. You are now an expert on MegaByte. I don't know. Do I have a summary? Let's see. So I like that you don't have to use a tokenizer. I think that the local model, global model is interesting because you can run these in parallel. It also simplifies. I think that you probably could have more levels of hierarchy here. I think you could have more global models, more local models at different levels. Maybe the only negative I find with this paper is that it's a little like they kind of fudge. They don't fudge, like they're not lying. The numbers are correct, but the way that they compare their model to the other models, it's like they're constantly kind of changing what their model is. It's like either like here they were saying, okay, we're going to use we're going to compare our model of 758 million parameters to perceiver of size 248 million parameters. That doesn't seem like a fair comparison. And then here again, they're also comparing their model, which is specifically for bytes, on perceiver on bytes, which again, I also don't think is a fair comparison. So they're doing a couple comparisons that I don't think are necessarily fair, but I still feel like, to me, this paper was interesting and kind of impressive, and they do introduce this new kind of idea where, hey, let's kind of break up the input into these patches, and then let's separate out this global local so that we don't have to run inference every single time just to get the next token. I feel like probably Facebook has a team internally that's working on this. The fact that this guy, Colin Flaherty, we looked him up on LinkedIn and he left Meta already to join a startup. Yeah, he left and now he's at a stealth startup. So there's probably a startup that's literally working on this right now. That's probably the startup this guy works at. So Facebook's probably working on a model for this, but it's not with the same team, so it's going to take them a little bit longer. They're probably going to be training this on a much bigger model. But yeah, I don't know. Excited to see what happens. Apologies for being kind of sleepy and tired today. Hopefully you guys were able to learn something despite that. Like and subscribe as always. Join the Discord. Feel free to come and talk some shit if you want. And if not, you guys have a great Thursday, have a great weekend, and see you guys later.